What up, mathletes? Woo woo! All right, let's do this today. Right here, we're continuing our study into graphs, analyzing relations. And so today I want to talk about looking at the actual graphs themselves in relations. Graphing the total time driven during your driving course can help you visualize the progress. A relation can be graphed without a scale on either axis to show the relationships between the independent and dependent variables. These graphs can be interpreted by analyzing their shape. So first of all, the values in the domain correspond to the independent variable of the relation. So here's what I want you to write down. The independent variable in a relation, usually x, has a value that is subject to choice. In other words, days. So this is the same example we started off with at the very beginning, if you remember, right? Nope, right here, I think. Let me get it loaded up. Yeah, right here, where we had a set of days 1 through 7 and a set of 7 driving times that corresponded to that. So like on day 1, she drove for 30 minutes. Now, we're going to put this in graph form and see what it would look like. And you'll notice it's saying we don't have units on this graph. We don't actually have to have units to analyze a graph. We can just analyze a graph sometimes. In this case, the independent variable, which is usually x, is the value that is subject to choice. So our x values would be days. And days is subject to choice because the driving time depends on it depends on the day, but the day doesn't depend on the driving time. So then we have the dependent variable, so that's the independent variable. Days are independent. They're independent. They don't depend on anything. The dependent variable is the y. So you want to write this down. Dependent variable is the variable in a relation, usually y, with values that depend on x. So if we look at the day will determine what our driving time is. So we can tell as we go from day to day, there's a bit of driving time this day. The same amount, and then we increased our drive. So we're seeing that we're increasing. We got some rest and going along as the days go along. And sometimes we have, when it's steeper, we had more driving time. When it's less steep, we had less driving time. Okay? So this helps us as we look and analyze the graphs of relations. All right, I want to get into some better graphs here as we go, because they do get better. The graphs represent the distance Casey, Jamie, and Anita have ridden on their bikes. Okay, so we're going to talk about that. So the first one says Casey starts riding her bike and then stops for a short period of time. So if I look at these graphs, this looks like somebody going really fast and then stopping for a long time. This is somebody riding their bike, stopping for a short time. Here's somebody riding their bike and stopping for a short time. So it's either one of these two graphs right here. She continues riding at the same pace until she slows down and rides at a slower pace. So this is somebody who starts riding, slows down, starts riding. Look, that's the same pace. Looks like this pace and this pace are the same, and that's what it said Casey did. Casey rode her bike at the same pace twice, whereas this one looks like somebody riding slow and then riding fast. And something else to help us, notice what happens at the end. It says that she continues riding at the same pace until she slows down and rides at a slower pace. So I'm pretty confident that Casey is rider B. Jamie starts riding his bike at a very fast pace until he stops for a long period of time. Oh, that tells me it's probably this, because that's a long stop and a fast start. That's a slow start and a short stop. So right away I know Jamal is right here. So, I said Jamie at first, Jamal, sorry. Then he continues riding at a slower pace, and we see that at the end is riding at a slower pace. And let's make sure, Anita starts riding her bike for a long period of time, then stops and takes a short break. So that looks like a pretty long period of time, short break. She continues to ride at a faster pace until stopping. Boom, that's definitely Anita. Let's check our answers. Hey, listen to that uncomfortable noise. Okay, I'd like to reset this slide. So that's how we look at graphs. And a lot of this, there's not going to be tons of notes here. There'll be some, though. Some example problems will help. Now, as we're looking at graphs, one of the things we want to talk about is scale. So you'll notice, look at the scale here. On the x-axis, right, every time I go over 1 unit, what happens? I'm only going over 1. It's grown by 1. So 1 plus 1 is 2. So we're just adding plus 1 each time on the x, right? So each time I go over, it's worth only 1. But what about when I go up 1 unit or down 1 unit on the y? It's going plus 5, isn't it? So let's see, from 5 to 10, again, plus 5. Okay, so the scale on the x direction is 1, but the scale on the y direction is 5. And we see that down here. The scale of 1 is that x direction, and the scale of 5 is the y direction. Although I typically on my graphs try to keep the scale the same, a lot of times our situations don't allow us to. So we have to be able to adjust our scale accordingly. But let's talk about how do we know how to adjust that scale? How do we even know what to make a scale? Well, there's a little bit of an art to it. It's not going to be perfect all the time. But here's what we do. So let's say I'm given these 1, 2, 3, 4, 5 points. And I'm going to graph them. I have negative 325, 4, 184, 9, negative 76, negative 8, 196, and 0, negative 181. All right, so let's look at our x coordinates. Remember, our x coordinates are just the first coordinates on each one. So if I'm looking at this, what are my x coordinates? Are going to be negative 3, 4, 9, negative 8, and 0. Now, out of all of those, which one is the least? Which one is the smallest or most negative? We'll see we have negative 3 is smaller than 4, smaller than 9. Oh, but negative 8 is even smaller, and negative 8 is smaller than 0. So our least x coordinate is going to be negative 8. Now, what's our greatest x coordinate? Well, it's not negative 3. All right, 4 is greater than negative 3. 9 is greater than 4. 9 is greater than negative 8. And 9 is greater than 0. So our greatest x coordinate is 9. Does everybody see that? Now, let's go ahead and talk about our y coordinate. So I'm going to highlight in blue all the y coordinates. What is our least y coordinate? Well, we have 25 is less than 148. Oh, now negative 76 is the smallest. And that's definitely smaller than 196. Oh, negative 181 is definitely the overall smallest. So my smallest y coordinate is going to be negative 181. And what's my greatest y coordinate? Well, let's see, 25 is pretty decent. Oh, 148 is a lot bigger. Bigger than negative 76. Oh, 196 is definitely bigger than negative 181 and everything else. So our largest is 196. Okay? So, I gotta write this down somewhere because I'm gonna have to put this all in computer. Negative 8, 9, negative 181, 196. So I'm gonna exit this out. I'm gonna write these in using the computer. What do we got? Negative 8, 9, negative 181, and 196. Check our answer. Look at that, we did it right. Which graph uses the most appropriate scales? Well, first of all, how many points are there? 1, 2, 3, 4, 5. This is the easiest way to eliminate some graphs. How many points are on here? 1, 2, 3, 4, 5. Okay, that might be it. So let's hold A there. This has 1, 2, 3, 4, 5. Now, here's what I want to say. Looking at this one right here on B, yes, it has 5 points left, but like this graph A. But doesn't A have them all spread out? Where this one has those numbers, the scale on the X is so big that it makes all our numbers look like they're right next to each other. So I would say B has all 5 points, but it looks terrible. Let's look at this one. This only has 2 points in it. It doesn't even have all the points, so we can X out. Okay, so right off the bat, I'm Xing out right here. 1, 2, 3, 4, 5. Okay, this has all 5 points, and they're spread out. Here's my one problem. Can I really tell what coordinate this is, or what coordinate this is? We have the x-axis, so it's grown up by 5 each time, so 5, 10, or negative 5, negative 10. And then the y-axis is just grown by 100 each time. So it's got so few values, it's hard to tell what these are, right? So because of that, I'm going to say, nope, not this one, and not this one. But let's look right here. So this is going up by 1, 2, 3, 4. So this is grown by 1 each time, but they've included enough values that I can tell this is clearly at 7 on the x. And then where on the y? Well, it looks like we're growing by 40 each time. So that would be 60. That almost seems like negative. So definitely like a negative 78. If I can get even close just by looking at this graph. So let's see, that looks like a 7, negative 78. Let's see if we can get another point as close as we can. This point looks like 0 on the x. And then negative 170. Were those two of our points? Let's see. So I have 7, negative 78, and 0, 170. I'm going to write them down. I have to erase these so I can move the screen. But 7, negative 78, and then I've got 0, negative 170. This graph's giving me enough information that I can guess pretty close to any of them. It's a much better graph. Let's look up here. Was there a 7? Not a 7. Oh, you know what? I said 7, but I don't want everybody to laugh. No, that looks like 7. Yeah, that's clearly 7. 4, 6, 7, 8. 7 right there. Is there a 7? I don't know. There's not. 7 negative, and it was going to be negative 78. Is there a negative 78? Oh, that's kind of close right here, though. 9, negative 76. Let's see the other one. Let's see if I got the other one. I had 0, negative 170. Is there a 0, negative 170? Oh, right there is close. But really, I don't know. Let's see. I think it might actually be this one right here. Even though I don't have enough, it might actually be more accurate. But let's see. Nope, I guessed it right. So it's hard to see a little bit, but this is definitely the correct one. I would say on the graphing right here, though, they made a mistake right there because really this point should be right here, and then I would agree with that graph. So I think there's just a mistake on this, but barring that, this is the much better scaled graph, okay? All right. Hey, I'm going to call out their mistakes. In fact, I'm going to have to write them on that because even though that was counted as correct and we see that, and I thought it was because it seemed the best scaled, we see there's a couple of errors. Like this one right here is supposed to be negative 181. That really should have been right here. So this graph, it's just like it's been shifted a little bit when somebody programmed it in there. But yeah, definitely the better scaled graph. We can see what numbers are. Okay, let's go to the next one. And now we've talked about describing the graphs. We've talked about being able to choose our scale correctly. Now I want to talk about choosing our origin. Our origin is that 0, 0 spot on the graph, right? So we've got our X, we've got our Y. Should have arrows on these, right? This is not a pretty looking graph, but I'm freehanding it with the mouse, so there is that. Our origin is right here. It's that 0, 0. What does our origin mean? It's important. If we're given data, we got to know what our origin means because it's going to change given the situation. So we have this situation. Scarlett opened her first frozen yogurt shop in 2010. Since then, she has expanded and opened more shops. The table shows the total number of frozen yogurt shops Scarlett has opened over the last year, or over the years. So in 2010, that's her starting year, she opened 1 frozen yogurt shop. In 2011, she now has 9 frozen yogurt. We see her growing and growing and growing. What should the origin represent in terms of the context of the situation? Well, if I'm talking about 0, 0 right here, let's see, should it represent the year 0? Well, if that's true, we'd have to literally get 2010 zeros before we get to any growth. So we don't want 0, 0 to represent year 0, but we probably want 0, 0 to represent the year 2010 and 0 yogurt shops. So if I'm looking at this graph, I'm going to draw something that looks a little bit like this, right? And up here we'll have like And since we're going from 1 to 98, I'm probably going to make each of these tick marks probably worth 5. So I'm going to be like every 2 I'll be 10, 20. And this would be a fairly high graph, right? And then over here, I'm just going to say, all right, I'm still going to say 1, 2, 3, 4, 5, forgive my sloppiness, and so on. But that doesn't really represent 1. If this is 2010, that would be 2011, 2012, 2013. So I'm going to let this represent my start of year 2010. And 0 yogurt shops. Now, that doesn't mean she has 0 yogurt shops in 2010, because some of you might be like, but Mr. Tim, it says she has 1 yogurt shop. That's right. That's why, right here at the origin, if I were graphing this, I'd put my first dot just a little bit above, right? Because she has 1 yogurt shop. Then in 2011, she's going to jump up here to 9. And then in 2012, she's going to jump up to 23, which is going to be up here. And do you see how we have this nice little, I drew that terribly, we have this nice little curve developing that's going to go up and up and up because it's going to be more exponential than not. So I would say this is most definitely be the year 2010 and 0 yogurt shops. Okay? You don't ever want the origin representing, at least on the y-axis, the dependent variable. So again, this is yogurt shops right here, right? Yogurt shops on the Y. Sorry, I can't write sideways with the mouse. And down here is going to represent years since 2010. Okay? You don't want this Y value to ever represent a number on the origin. It needs to be 0. Whatever your y-axis is, on the origin, it needs to be a 0 for the Y. Okay? All right. Go ahead and write that down as notes. And I'm going to erase it. Pause it, go back and pause it if you need to. And let's go next. So our last deal, we're going to kind of combine these 3 skills. Pardon, my voice is raspy today. I'm not totally sure why. And it says the average number of posts per day on a social media site each year is given in the table. Interpret the meaning of the axes, scale, and origin of the corresponding graph of the data. So if I'm looking at this right here, right? So first of all, what do we see on the X? We see years since 2008. So that means year 0 is the year 2008. And you'll notice, kind of like what I was saying, where the 1 yogurt shop was just a little bit up at year 0. Well, at year 0, we see a little bit up here, which tells me that that represents the 15. And don't forget, what does this say? In millions. So when it says 50 here, that's really 50 million, 100 million, all the way up here, 650 million average posts per day on the social media site. So the y-axis, the origin, is not only the years, it represents the years since, or it represents the year 2008 and 0 posts per day. Okay, but on 2008, they didn't have 0 posts per day. That's why we're up here just a little bit, because there's about 15 million average posts per day. Dang, that's crazy sauce, man. And then what does it want to tell me? It wants to know about the scale. Well, the scale we see on the x-axis growing by 1, which is just growing by 1 year, and each year since 2008. And then we see that the scale on the y-axis is growing by 50. 50 to 100 plus 50 to 150, and that represents average posts per day in millions. And we already talked about the origin being, that represents the year 2008 and 0 average posts per day. So, nothing too earth-shattering. You should be able to crush the rest of your assignment if you haven't done so already. With that said, peace out.